Okay, a quick tutorial to help you with some of the Groundwater Lab questions that you might have. So, what you're seeing here is the beginning of the Groundwater Lab. Now the good news is we're not going to use Google Earth, so if you struggle with that, then you're like, okay, we don't have to do that. The bad news is there is some math in this kind of lab, but it's not that crazy. If you take your time and just kind of follow what the equations are telling you to do. So the first part of the lab starts out with 3 different maps on 3 different time periods. So the first one, this figure 12.3, is from 1946. And all the dots that you see are wells that are drilled into the ground. The numbers that you see is the elevation of the water table at that location. And those values are given in feet above sea level. So what you want to think of those as is an elevation, and if you compare to the one next to it, a higher number, right, means that the water is higher up on the well. A lower number, the water is lower in the well. And so we want to compare how the elevations in the wells have changed over time. So here we have 1946. If we scroll down, we have a 1976 data set, and then we also have a 2003 data set. So there's a couple questions that just ask you, okay, based on what you know about the water table, where is the water moving to in each of the particular maps here? So just as a kind of helpful hint here, right, if we go to 1946, what you're looking for is a low spot. Where are the lowest numbers? Because remember, you can treat this data like almost the surface of the earth. So the water is going to flow from high to low. It's just like if it was the surface of the earth and you poured water, it's going to flow from the high points to the low points. So as you look around this entire map, you could see that there's higher numbers up here to the north. There's lower numbers and the lowest here to the south. And so when rain falls into the ground and soaks down and hits the water table here, the water in the ground is actually in motion. So it is flowing, in this case, mostly to the south. It is flowing from up here to down here. If water fell over here, it would flow down this way. So it's really flowing to the low part, in this case, of the topography, which mimics the water table, and that is something that we typically see. If the land surface is sloping, then the water table slopes the same way. And in general, the low area is the Salt River. That's why the river is located there. And so in the subsurface, we see a similar trend where the water moves from north to south. So that's what it's asking you to do in these second two. Now the low numbers have moved. So they're no longer the lowest are down here. They're somewhere else. It is your mission to find the lowest number you can, and then that would tell you where the water would be directed to. So we've changed the way the water moves in the subsurface by altering, potentially, right, how much water we take out or something, and that's maybe part of what we want you to puzzle out in the lab. So you'll do that for the 3 different maps, ask about why that might change, compare points, right, point A to point C from the different maps and see how much water has increased or decreased and potentially why that might happen. Here comes some of the calculations. So some other information that's useful is what's called the hydraulic gradient or the gradient. Now, gradient is something we talked about when we did topographic maps, and it's the same thing. It is the slope of that surface. Instead of talking about the surface of the earth, we're talking about the surface of the water table. We still calculate it the same way. We need 2 points. We need the elevation of one point, the elevation of the second point. We're going to subtract those two. And then we're going to divide it by the distance between those 2 points. And so the elevation is usually in feet. So we subtract that and we get feet on top. And then we get the distance between those 2 points, and that's in miles. So our answer is in feet per mile. So we might get something like 50 feet per mile. What does that mean? It just means that over a mile, you will change 50 feet in elevation. Now, of course, because Canvas is a little weird, We're not applying the units, just the number here. But it's asking you to do this trick, right? So A, B, you need a couple things. What's the elevation at A? What's the elevation at B? And you need the distance between those 2 points. Look, you're estimating. So if we go way up to here, there's A and B. Elevation, elevation. Piece of cake, you subtract. How far apart are they? All right, there's a scale here. So you're estimating how far apart they are. Look, it's not the most convenient way to do it, but you could grab a piece of paper and hold it up to your screen and put some tick marks at the 0, 1, 2, and 3. And then you'll just hold it from A to B and estimate it. Is it 5.5 miles, 6 miles, 7 miles, 20 miles? Right? So get a reasonable estimate for the distance. Then you have the change in elevation, the top part of your fraction, and then the distance in miles. You just do that math and you'll have the gradient. The good news is the distance between the points on all 3 of the maps are the same, so once you measure it, you already have that distance. You don't have to remeasure. It's just the elevations are different. Okay, let me scroll, not too fast to make you dizzy, but down to the next part. So here you're doing those calculations for gradients, asking you to compare those. And then there's more information that we can gather from some properties of our groundwater table. And so one is to figure out how much water is available to us to pull out of the ground to use. So here in the Phoenix area, we use a lot of groundwater because we don't have a lot of surface water. It'd be nice to know how much we have available to us. So there is a way we can calculate that. How big of an area are we talking? And so what we're doing in this equation is we're getting just the area, so the length and the width. So we're going to assume that the layer, right, the rock layer or the sediment layer that is holding this water, which means it has some porosity, that when water hits it, it can soak into it and be stored in those open spaces there. We want a shape. Okay, so we're going to assume that we have kind of like rectangles. So we get a length and a width. That gives us some component of the area, but we need the thickness to get the volume, right? So we need a 3-dimensional rectangle, like is in this image right here. And what we want you to calculate is, what is the volume of this 3-dimensional rectangle? We can then use that to figure out how much water is in there. So in this example, we give you the length and width. So you go back and you calculate the area, right? It's just 9 times 12, right? That's the dreaded formula for the area of a rectangle. We do have to convert that, so be aware there's a conversion factor up here that tells you to change your miles that you just calculated, your square miles, into acres. You can do that by multiplying by 640. Bam, you got this first part of the equation. Now, remember that this water table is below the surface. It is not floating on the surface. It is not the same elevation as the surface of the earth. It's down into the earth. We have to drill down to get it. And so that's what this is telling you here. You have to drill down 300 feet before you hit the top of this rectangle. And then how far can I drill and still get water? Because at some point, as we go deeper, there's a point where the water can't penetrate. And so we need to know the thickness. Well, we're telling you it starts at 3 and ends at 1100. You've got to figure out how thick that is. That is this part of the equation. So I have acres, I have thickness. If I multiply those two, it will tell me the volume of this entire 3-dimensional rectangle. But the entire rectangle is not full of water. It is full of sediment. And it has some open space that's full of water. How much? Well, 13% of the entire space is actually full of water. So then that's why we multiply by this third part here, the porosity. Remember, if you're just putting in numbers, you want to put 0.13 if you're using a decimal form of the percent there, right? So you take those values, and that'll give you an answer. It'll be pretty big. It'll be in acre feet, which is a unit we use to measure water. And an acre foot is just covering an acre a foot deep. That's what 1 acre foot is. And so once again, just put in the number here because Canvas is weird about how it interprets certain things. But that'll tell you how much water is available in this unit here. And then, of course, how long is that going to last if we pump out this much every year? So you could tell me how long that water lasts before it's gone. And then we're going to do something similar. So look at a similar rectangle. We're going to change where we drill the water from and change the porosity and see what we get for an answer. Compare that and see how the effect of porosity is impacting the amount of water we have in our aquifer. Okay, let's see. This part I think is pretty good. It's just how deep do you have to drill to hit the water table, so that shouldn't be too challenging for you, I hope. The last part, once again, we're looking at some calculations. So I don't want you to get overwhelmed by this. So you're just kind of putting some values into here and putting them in your calculator to give you an idea of how you could calculate some of these things we're looking for. So here we're looking for the groundwater velocity. So how fast is the water moving in the subsurface? Because what we want to figure out is if there's pollution that gets into the groundwater, we want to know how fast it's moving, because we want to try and get in front of the plume, as we call it, so that we can do something to extract it. A lot of times we drill wells ahead of the plume and try to suck out the contaminant. But if I don't know how fast it's moving, I don't know where to put my recovery wells and things like that. Okay? So there's a couple things we need. The hydraulic conductivity, which we really don't talk about in this class, is just a value that we're giving you. So you're just going to plug that in here. And then this is just a conversion. This is just a conversion. So really all we're doing is taking the hydraulic conductivity and we're multiplying it by the gradient, how steep that water table is. Those two things will help me figure out the velocity. The other two numbers here are just changing the units, so it's going to come out into our feet per year answer. Okay? So now look, you've already calculated the gradient I want you to use. You just go back to question 10, and that's the number you're going to put in here. Okay, so put the number in for your gradient, divide it by 5,280 first, so you'll get this value. Then multiply, multiply, and bam, you should have an answer that's in feet per year to tell you how fast the water's moving in the subsurface. Okay? Now that I know that, how fast it's moving, I can tell you how long it'll take to get somewhere. Okay, so if I, in this case, wanted to know it's going to travel from E to F, well, how far is that? Once again, you know that distance. We've already measured it for gradients and things like that. And so you're going to put that in here in miles. This is, once again, a conversion factor. It's changing to the units that I want it to be in. Okay. And then the groundwater velocity you just figured out here. You plug that in, and it'll tell you how long is it going to take for some contamination to travel from well E to well F. Okay. And so this is stuff that hydrologists would do, right? We're drilling and testing wells looking for contamination. If it's discovered, we want to figure out where it's going and how fast it's going so we can come up with some solution. So the last is kind of an example. Let's say we have some wells drilled here and we look at some data. So now this data is telling me contamination. A larger number is telling me more contamination. A lower number is telling me less contamination. The problem with this data set here, as I look at it, is that there's a high concentration in the middle, and there's a low concentration near evil electronics, and also a low concentration near mad microchips. This data isn't very useful for telling me who's doing the contamination, but you know something about what's happening in the subsurface. What we want you to do is use your knowledge of how the water is moving in the subsurface. Okay? And so what you're going to do is go to the 2003 map that's at the top of the lab and determine which way is the water flowing. That should tell you who is polluting based on the motion of the water in the ground. If I put contamination in a certain spot in the ground, it can only go one way. It goes from high to low. So you should be able to puzzle that out using your knowledge of how the water's moving in the 2003 document or map that we have at the beginning of the lab. Okay, look, the next thing you're going to calculate is just what we did up here, which was kind of a practice run, right? E to F. Now, based on who is polluting here, I want you to do the calculation again, okay? So what you're going to have to do is figure out who's polluting, and it's heading toward well G, right? So G is up here. Who's the polluter? And then we want to figure out where is it going and how fast and all that kind of stuff, right? So you're going to go and estimate the elevations at a couple points because we need a gradient. In the previous one, we were using the gradient from question 10. Here, I want you to calculate a new one. The distance between the 2 points, the polluter and the well, and you'll have to estimate the elevations. You can do that by looking at the map from 2003. If there's a number that's close by that has an elevation of, 1045, then if it's really close, it's probably similar to that elevation, right? So get those two values, subtract them, divide by the distance, and you have a gradient. You're going to just plug it in right here. So that stays the same. That's a conversion. That's a conversion. You plug in your newly calculated gradient that you just acquired from the 2003 map, knowing who's polluting and where the well is that I'm concerned about. You're going to get a velocity, and then you can tell me how long it will take before that, or how long has it taken for it to get to a certain point, right? And holy cow, we made it. Okay, so I know there's some math in there, but really there's a lot of math in there that's just altering the units. Right? So there's a lot of conversion factors built in because I know it's challenging at times to change units back and forth. So take your time, work your way through it. Any questions, as always, send me a quick email if you're not sure how to do the math in something. But yeah, so no Google Earth. You got that going for you. All right. Good luck. Have fun.